Hello, everyone. I want to say thank you for all being here, and especially thank you to Thomas, Sydney, and everyone else for helping to organize this. This is really excellent. How many of you within the audience work for Google? Just because I feel like most of you are unfamiliar faces. Okay. So yeah, very good to meet folks outside the community or whatnot. So thank you for all coming here. So I'm Matt. I work here at Google Zürich. I'm going to give a talk about a feature in the standard library related to testing that, in my opinion, I think hasn't gotten enough attention, or at least I think it's kind of cool and offers some pretty cool facilities. So without further ado, so genesis of this talk. I wrote a blog article about 6 months ago. It's basically about this topic. It's much more in depth, but I figured this might be kind of a cool little introduction thing, maybe for, especially even for some folks who aren't super familiar with Go, because this is some pretty cool power that I think might be, I find pretty compelling for working with the language. So this talk is available online right now. So I mean, I'm happy to see none of you have your phones out or your laptops out, but if you were interested, you could grab it right here on this AppSpot address. So it's there for you later. Okay, so let's talk a little bit about the cast of characters. So how many of you here have actually done a fair bit of coding in Go? Okay, so that seems like it's about half of you. And among those of you here, how many of you have actually used the testing facilities? Okay, that's about almost 1-to-1. I'm very happy to hear that. For those of you who are new to Go or haven't actually done a whole lot of testing, you'll be happy to know that there has been a lot written about how to actually do proper testing in Go. And I guess what I'd say is, like, I'm happy to say that also, like, a lot of what has been written hasn't been necessarily super religious, and a lot of it's very down to earth. Like, there's no need to really grok like major heavy frameworks or whatnot. So I've given you a few links here if you're interested in how to do testing in Go, and namely some of the practices. A lot of that is really kind of going to be the building blocks for this talk. So those of you who have done Go and have done testing, how many of you, separate from this talk I've titled here, have actually heard of this package here, Testing Quick? Okay, only actually one of you raised your hand. Okay, so then this is going to be really introducing you probably to something new. How many of you come to the table with having done anything at all in Haskell? Okay, so there looks like about 8 of you. Okay, those of you who have done stuff with Haskell, have you worked with this package called Quick Check before? Okay, so a few of you. Okay, so this will be pretty familiar for you in some measure if you've come to the table from the Haskell world and have used Quick Check. So new suspects, as they say. So for those of you using Go, this is pretty cool. Did you know that Go can generate arbitrary values for types? So these are not all the types, of course. I wanted to keep everything fitting into the slides. So this is just a quick synthesis of, like, you know, the gamut of built-in types into Go. Did you also know that Go could generate values for arbitrary types, even the ones you make? So I built this type here in this slide, point. I wonder, could I have the language actually build me an arbitrary value for this? Let's click run and find out. Wow, it gave us a point with an arbitrary value here. So those of you maybe not super familiar with the language or having used reflection, let's talk a little bit about what's going on here. We initialized a random number generator. I'm just doing this just so this example is deterministic. We are using the reflection library, which allows us to get information about a type. And basically, we're just getting the type descriptor for this point here. Quick, this is that package I'm telling you about, which is a sub package off of testing. What this is doing here is I'm passing in the type descriptor and the random number generator, and I'm saying, I want you to attempt to generate an arbitrary value for this type, which is what we saw when we ran this. So I'm not actually pre-initializing this with anything. So this is actually using the runtime reflection methods to generate arbitrary values. So the real meat of this is this function here, which is part of the testing or quick package called value. Basically, what the signature has going for it is type descriptor, which we pass in as the first argument, the random number generator. What does it return? It returns then a reflection type called value, which then describes the actual underlying value. And then OK, which is, as Thomas was talking about in his slide, well, Go has a convention of often using a error as a second return value, or OK as to say, like, well, was this possible or not? So OK is just kind of a sentinel of saying, was something able to be generated here? So that's how we did this. So let's continue for a moment. So how does this work? And by the way, if anyone has any questions, please don't hesitate to just like stop me at any point, raise your hand and ask, okay? So how this works under the hood is this is basically like white noise generation, if you will, for these arbitrary types. So there's really not that much that's all that intelligent going on under the hood. It will look at the type using the reflection mechanism and say, okay, for the given structure of fields or whatnot, can we just generate something that's just arbitrary for this? It just at least fits the type contract. So I have a custom type here, and Thomas talked a little bit about building custom types. So I have a type here to represent stooges, like the Three Stooges. So, and we knew through the course of the whole series of the Three Stooges, there were, well, more than just the Three Stooges. There were several, depending on like whether who was alive or whatnot at the given time. So we have basically here this enum of sorts, this is kind of like a Go idiomatic way of representing an enum of a stooge. So let's say we want to arbitrarily just generate a stooge. Well, if you have a type that fulfills this interface here called quick generator, you have the ability to actually randomly just generate something that fits with some sort of type specification. So let's see, we want Three Stooges. We don't care who they are, but just give us Three Stooges. Voila. And this actually falls back onto using this generate method here that has been attached to this type. And we just basically say, just give me any sort of arbitrary stooge that's within this range. So does that make sense for everyone? Okay. So back to that previous slide where I showed you, I said like, okay, let's take this type of and then like do this reflect value stuff. To be honest, the reflect package is something that most regular Go programmers don't use on a day-to-day basis, and it's a little clunky, but it does its job well. Often if you want to construct a type literal, I try to distill like the common classes when you would want to do a type literal right here. I think this might be kind of helpful for reference for offline for folks. It's not super critical, as you'll see later on, but this is just one of the building blocks. So like if you wanted to get actually the type descriptor for like, say like a standard value type, that's what you'd use. Pointer, a standard exported type like HTTP dir, an anonymous struct. Thomas, did you talk about anonymous types in your talk?
Just mentioned unnamed and named types.
Okay.
I haven't mentioned anonymous structs.
So in Go, you have the ability to actually define types within like function closures. They aren't method. You can't actually make, you can't actually attach methods to them, but you can effectively create like unnamed types on ad hoc basis for like serialization and whatnot. So like that's what you have right here by anonymous struct. It's just unnamed. It just represents whatever values you assign to it. So let's talk a little bit about quick values limitations for a moment. So the first thing to note is, and this is completely a limitation of the actual quick value function, is that it will only actually generate values, arbitrary values for structs or any sort of child object related to that type if all fields are exported. And in Thomas's talk, he talked about saying something is exported if it's capitalized. If it's uncapitalized, it's basically private or not visible to foreign packages. So this is purely an artificial limitation, but this is just something to be aware of. Let's go a little further for a moment. Thomas talked about what channels are. So let's say you have a structure or struct or something that has a channel in its actual definition. Quick value can't generate just a random channel for you. This is actually purely artificial again. I have an open change list actually to add that support for that, but I haven't seen that for review yet. Another thing is, how many here have heard of the Go Oracle before or know what it is? Wow, okay, only 3 of you. So if you're new to Go or you're just getting started or otherwise, the Go Oracle is a really cool tool. It sits aside and basically helps you with your workspace management of sorts. What the Go Oracle lets you do is the Go Oracle scans your workspace, effectively the transitive closure of your build project. And it generates basically a description of metadata associated with all the things it's able to scan. Like let's say you have an interface like reader, and you're like, well, I would like to know what types within my workspace fulfill this type. Well, you can ask the Oracle, and it has a query language associated with it. Emacs, Vim, I think even a few other editors have integration with it. So you can effectively say, I would like to know what types fulfill this interface here based off of my workspace. It's really handy, and it's quite fast too. It's actually part of the, well, it's not part of the formal Go project, but the Go authors themselves have actually helped build it. So it's I should say, like almost like a second-class citizen in the Go world. It has a lot of other things too, like so Go supports like type inference and whatnot. So you could say like, well, what type is this thing where my cursor is right now? Or given the data flows for this function here, what possible concrete types could it be? It can give you answers like that. So it's pretty cool. So with having said that, the quick value mechanism can't actually just give you a random type that fulfills a given interface. I wish it could, but there's no mechanism in the actual user-exposed runtime of Go to say, well, we know that all these types fulfill this. I suppose you could probably expose that somehow, but you know, on the other hand, you never know if that's ever going to be correct or not. So that's a limitation to be aware of. Another thing too is, let's say you have a data structure that has, well, some sort of structural expectation to it. Like let's say you have like, you know, a graph, or you have something that has like some sort of topological consideration, like, you know, is it recursive, it's cyclical, what's the completeness? Well, quick value can't take that into account. It's just going to just generate, as I said, white noise. If you have a specific way you want to represent an object, just implement the quick generator for it, and you know, you'll have your way of generating it. Other thing too is it can generate unsafe pointer, and Thomas did talk about this for a moment. The Go spec allows you to cast the unsafe pointer back to other types, and you can do some obviously unsafe things with it. So if your type has unsafe pointer embedded into it, like a struct or otherwise, it's probably not a good thing to work with the quick value, because you probably result in memory corruption or otherwise. So why am I mentioning these limitations for a moment? These are the building blocks that are going to segue into this whole topic of fuzz testing and otherwise. Now, this stuff might hit home a little bit more. CGO, SWIG, code generation, vendored code you're importing. If you're going to use the automatic value generation, these are places where these caveats I just mentioned to you are going to matter. Like if you're importing a foreign type and it has unexported fields, or if it's doing like something with, say, CGO or whatnot, these are places, like all these caveats I mentioned are going to come to the fore. How many here use protocol buffers with Go? Okay, so I see a few of you. Okay, sometimes I've used the value generation stuff just to generate arbitrary values for, say, you know, sanity testing or hardening. Well, unfortunately, just due to the way the Go protocol buffer implementation is, which it's pretty good, there are some internal fields within there that, if you use arbitrary generation, will effectively result in semi-corrupted messages, even if they're otherwise correct. For testing, I actually generated a public helper here that will basically go through and recursively renormalize the protocol buffers. So this is one way you can get those to work correctly. So let's continue on. Other things too. So I mentioned this quick generator interface. I haven't actually ever seen any sort of exported type out there in the wild that implements this. A couple of notes. If I were building a type that's public, I don't think I would publicly implement this interface here, partly because, well, it pollutes the API. Number two, if any user wants to ever use quick value or any sort of fuzz testing mechanism, they're locked into your implementation you've provided right there. And you know, as we get a little further on, you might see that like you really wouldn't want to exclude users from one sort of implementation or another. Actually, I was going to say it here on the bottom. If you have a private type, or sorry, it's unexported, feel free, go right ahead. You know exactly what you're doing with it. So now that we've talked about value generation, let's get to fuzz testing. So basically, what this is about is enforcing an invariant, or set of invariants. So let's define an invariant. So basically with an invariant, we're saying that like, well, given some sort of set of operations, we expect some sort of set of conditions to always be held true. So I think that's probably about as simply as we could say it. So let's take a very simple example. You know, we have simple mathematics here. You know, we want to like check out the commutative property of addition. So you know, a plus b is equal to b plus a, right? Okay, well, is there a way we could just always say, is this property enforced? Well, it turns out the testing quick package offers a quick way of doing this called check equal. I'll talk about what that means under the hood in a moment. But we've defined two functions here. Function f, which takes arguments a and b, integer, returns an integer, and does a plus b. And we have g, which does basically the same except for, you know, reverses them. Well, let's see what check equal tells us. Are there any counterexamples to commutative or the commutative property here? Let's run this. Well, it says there aren't. Under the hood, what this has done is this has executed functions f and g repeatedly for many values that's generated arbitrarily per that previous section I just talked about, and says, are there any for which this thing does not, or like where the left-hand side is not equal to the right-hand side? So this is pretty useful in certain cases. So counterexamples. Well, is division commutative? Let's find out. So in other words, is a divided by b equal to b divided by a? Well, let's see. Let's find out what happens. Oh shit, this thing says we're throwing up smoke. This property doesn't apply. So let's dissect what this means. So number one failed on this input, large integer, large integer. So this first integer here is a, this second integer is b. And then it says the output here from the left-hand side is -1, and the output from the right-hand side here is 0. So this allows you to actually see like what was evaluated on as input and then the respective outputs for which this wasn't true. So this is a pretty cool feature, I think. So let's talk a little bit about what's going under the hood here, and we'll by exploring the method signature or the function signature here. So F and G interface. Well, unfortunately even the documentation I found when I read this, I wasn't super satisfied with it. So I'll just quickly spell this out in layman's terms. So F and G are functions that have equivalent signatures, both argument and return, and they have to be that way. So, and then config is obviously the configuration. To be honest, you can read the Go doc on that, and it's pretty self-explanatory. And using this facility, we want to say, using reflection on F and G, let's determine what types of arguments they take, and we'll just generate, for every actual argument they take, respective permutations or variations of that, and see if there's any case for which, G for these arguments is not equal to F for these arguments. Simple as that. And again, I guess I should say the caveat being is all the arguments have to be generatable by check quick value, which is why I spent all that time talking about those inputs and what works. So let's see. You're like, well, guys, I've come up with this awesome sorting algorithm. I think this is going to be the best thing ever. I think Rob Pike is just going to smile, when I propose to replace the standard sort mechanism and go. So you're like, I want to first of all make sure that this thing is correct before I send in a change list for this. So I have my function implemented here. And for those of you who are not super familiar with Go or with the sorting package, the sort interface here is basically a type that fulfills the requirements for sorting, which basically how is this type? How is value, or the left-hand value versus right-hand value, what's the ordinal placement, and how to do swaps for the given data type. That's all that this is. An int slice is an internal type, or a type alias, I should say, within the sort package for like a slice of integers that fulfills this. So what I'm interested in doing is the function f is the reference implementation using sort.sort, and this is part of the actual Go standard library right here. And in a moment, I'll talk to you what this rest of this boilerplate is all about. And here's my bubble sort. Now, in reality, I needn't have defined this as actually like a local function, but this is partly a quirk of the Go present tool. So let's run this and see if these things are always equal to each other. Well, I'll be damned they are, but in reality, the bubble sort isn't so fast. So I don't think Rob Pike would be very happy with it. So let's continue on. Okay. So the check equal, I think, is probably one of the simplest ways of just doing like invariant testing in Go. So when is this thing useful? I personally like this thing when I have a known good implementation or reference implementation of something, and I want to check it up against a a proposed one or something experimental. Like it's a very nice, fast way of doing it. So how does this thing work under the hood? And are there any caveats to be aware of? Unfortunately, there are. So in Go, a nil slice is not strictly equal to an empty slice, even though the mutation operations with append, length, capacity, and whatnot effectively act like the same. They're not the same. So reflect db equal will say that if one side has a nil slice versus an empty slice, they're not the same. Same thing goes for a nil map versus say an empty map. And to be honest, I think that's really where like the bigger, like the way you're going to encounter more runtime problems will be. So these could be like little trip points you should be aware of with respect to the function implementations, because the quick value thing uses reflect deep equal under the hood. So I personally wish that the check equal in other facilities would actually give you a more nuanced error message that talks about explicitly saying like, well, this component here was not equal because of this or something like that. But that's a topic for a later day. So another thing to be aware of is with the way the F and G are called using the reflection library, the values or the arguments for F and G are actually the same, and they point to the same space in memory. So if either F or G mutates the arguments, well, you're going to have some complications with your test. So back to this example here, I just, outside of the scope of this thing here, I just wrote a quick function that just defensively copies the data. That's why, because sort actually mutates the data in place. Does that make sense so far? Okay, so let's continue. So there's the second thing, and I think this is actually pretty cool. And this is called the quick check function. Now this supports all sorts of invariants. Like, to be honest, any of the invariants we defined with the check equal could be completely represented with this. This really is the Swiss Army knife of doing like just fuzz value generation. So very similar story to check equal. Like the same kind of caveats apply about the argument generation. So the fundamental expectation is this: F can be a variadic function. Any argument it takes has to be able to be generated by quick value, but it has to have a unary return signature of a bool. And the value of the bool return signature just simply means like, if the value is true, all the invariants that we've identified pass. We're good. If it's false, oh, something broke. Let's short circuit the test, and we've identified a input for which some invariant has been violated. The report you would get about the violated invariant is basically very similar to that other one I just showed you where we tested the commutative property on division. It would basically say, well, this argument on this iteration count. And yeah, and that's all they would actually tell you. It's not super informative. But the overall pattern of how the usage looks like is something like this here. I just wrote this in. So those of you who are not super familiar with Go test, or like just testing in Go, this line here and this line here are basically the common boilerplate you would see on a test function. The t type here, or I should say the t value, is the local state of the actual test context. And like this is how you'd signal to say like, oh, we've encountered an error, let's abort out of here or something like that. That's the standard way of doing it. Now, for the parts that's specific to quick check, you would normally define a function within this, or it could be external, it doesn't really matter, that basically orchestrates, getting everything in order for the test, actually exercising the system under test, like actually executing the thing that produces the side effects, and then you validate the invariants or assumptions. Now, this needn't be strictly how every actual test function looks. You could technically have it be, you set up your context, you do one operation, check invariance, do another option, check invariance, until the cows come home. It's pretty flexible in that, but this is just like one quick pattern. And at least in the test context, often you'd see something like this. Run quick check. If the error, is not equal to nil, that indicates we probably had a violated invariant or a bad assumption somewhere. Let's report that. So where does this thing come in as helpful? Well, if you're writing decoders and encoders, this can be quite helpful if you have the ability to like do bidirectional operations with it. I wrote a delimited protocol buffer, a linked delimited protocol buffer encoding scheme. I'll show you very quickly here. And it has tests associated with it, but this thing should jump to the line. My apologies. Okay, right here. So I can't use quick value to generate the values here, but I have a separate mechanism that generates them for me. This basically just gives me a slice of random protocol buffer messages that have been filled out using quick value under the hood. I write them out to a byte stream here on byte buffer, and then I just read them, and then I read them out using read delimited. Now, each step of the way, well, actually here, you see some error reporting here where we just simply abort out if we encounter some sort of problem writing. Now, we say, let's start reading them out. Let's make sure that the left-hand side is equal to the right-hand side for every message we've actually streamed to this buffer. And we're doing that. And then if we encounter something that we don't like, we just simply bail out here with this fatal. I actually should have just had this thing return false, but I was kind of sleepy when I wrote this thing. So this was many moons ago. So you can see this is basically a quick way of end-to-end just passing in all sorts of garbage into this encoder and seeing if I'm able to get back out exactly what went in. So encoders are one place you'll see this used. Like in fact, if you look at the standard Go distribution, you'll find this used probably about 25 places or so in places related to encoding. So also places where you have very discrete requirements or assumptions about inputs and outputs, or where you can quickly determine that based off of arbitrary input. So if you have a public API, I think this is especially useful because you never know what your users are going to throw at you, and you want to make sure that you don't blow up in an unexpected way, or at least you return a meaningful error back to your user. This is not the end-all be-all for malicious input, but I think partly this point above allows you to capture this. Now here's another place where I think it really is magical. Let's say you have something that's probabilistic, and you're like, well, how do I build tests for that? You could build, your very case-by-case TDD-oriented thing for it, but at some point you hit this case below in a way where you're like, well, I have a large number of inputs and I have a large number of expected outputs. Is there any way I can rationalize and simplify this? Well, my friend Sean wrote or implemented a streaming quantile estimation algorithm, and this algorithm has a couple properties associated with it. It says that I will guarantee for certain memory requirements that the error or that the error of the estimation is no more than whatever I allow it to be. So what he did was he defined this Go test here and said I wanted to make sure that the actual respective error for the 99th percentile is this. So he built himself this within error function that basically just generates some arbitrary values, and it then says I want to actually just validate a couple of invariants with this. And as we see here, let's see, the fits. So this fits part here is actually what does that quick error estimation with that. I don't want to have to go and show you the whole code here. I mean, if this is too small for you to read, let me know. But so this is the part here where he actually does that quick thing, like does this actually fit this estimation? And what quick check does under the hood is it just generates all sorts of arbitrary values that it throws at this thing. And he's basically saying, I want to make sure that always within, no matter what input I get, that the actual respective error rate is always within this allowed tolerance. So, and if it's not, you can see that we just simply return whether it is or not, and then boom, we're done. Okay, so those are some of the really handy places where you can do that, because to be honest, I like table testing and otherwise in Go, I think they're really handy. But sometimes, when you get these combinatorial inputs where they're just so onerous, you just want to be able to simplify it, and I think this is really powerful. So another thing, my friend Richard, who works in this office, implemented a skip list. This is another probabilistic data structure. And in this case, unfortunately, well, I have a list. I wrote a simple invariant test here. So right here, we just quickly have, this is passed into quick check here. This basically give me a slice of arbitrary integers. I then say, well, I have a reference copy of so the skip list is actually a ordered data structure that you can traverse relatively efficiently, but the probabilistic bit is how it's indexed for traversing itself. So I'm basically saying I have an expected set of sorting order, which I'm going to let sort do here. I assume the actual sort package is going to do this correctly. Great. And I then say, okay, I'm now going to actually add this to my skip list. And now what I want to do is I want to make sure as I iterate over every value of the skip list that it corresponds one-to-one with the actual sorted list I have. So, the first thing we do is we make sure that the actual number of items we've encountered is not more than what we've actually put in there. Next thing we do is we say whether the actual values match. And at any point where this isn't, we abort out. Now, one thing what I want to show you here that's important is, and I'm going to talk about this on a later slide, is good technique. And the good technique is when you have a violated invariant or assumption, you should make sure that your actual test reports what was violated, where and why, and what it means. Because as you saw on the previous slide, if it just tells you the inputs and outputs, well, what does that mean? Why did that break? Well, having this information like these log messages here, or the t.errorf, that's really helpful for understanding like what was broken or why. So let's go back for a moment and let's just run this. I found a bug actually on the local app engine thing, so this might not work. Oh, there we go. So we were able to say for all sorts of values of integers in a slice that while traversing the skip list, they're always ordered exactly like a sorted slice is. And we're almost done here. So yeah, so basically what I just told you there about having that special error reporting about those contexts, that's pretty helpful. Okay, let's talk about other things that do things kind of similar to this. So Dmitry Vyukov, he works on Go, I think, part-time. Mostly he works on the memory and thread sanitization projects here at Google. You might have seen him actually write a few publications or whatnot. He discovers some pretty fun problems in Common Code. He contributed the race detector to Go and other things. So he wrote this nice tool called Fuzz. Fuzz is relatively modern. It does relatively similar thing to what we see here in Testing Quick. If I understand correctly, it can run both on a local node as well as on a machine farm. And unlike Testing Quick, it does have some ability to apply learning to the actual data set, where you say like, well, this produced an error. Let's see if we can try to localize it around other problems related to that. It's pretty cool. I guess the question is when to use what? Testing Quick has been around with Go since 1.0. Fuzz has been on the side. I think it's a fantastic project. It's found plenty of bugs in Go and other projects. The question is like, which is like lighter weight for the, like, do you care for a lightweight or heavier weight solution? Up to you. So that's just another alternative. I actually got started in software. Now I'll talk about what this means here in a second. As a test engineer many years ago, working on medical software. Basically, we had software that was used for tracking the workflow, or I should say life cycle, no pun intended, of patients in a hospital. And my boss at the time was a really nice mentor and really good guy. And I remember one of the first things he had that I really scratched my head at, because we're building basically automated test suites to validate stuff. And like one of the things he was like, so I have this stochastic monkey test. And I spent a lot of time looking at this thing because this thing was built in like a derivative of a Visual Basic made by Microsoft called Microsoft Test, which was then bought by Rational Software. It was basically Visual Basic with pointer support and some other funny things like that. And so it allowed you to kind of do some terrible things like this. So, but basically what this thing did was, it was like, well, I know the application starts in some sort of known state, and we can apply certain transitions and bring it to states A, B, C, and D. And then from those states, there's again another set of transitions we can apply for various sets of inputs. And then each set of the transitions, it would basically validate certain invariants. This piece of software we had was terrible. It drew directly to the Windows GDI. We did basically the invariant testing by doing regional or sectional screenshots and then doing byte differences with this. And Microsoft Windows font rendering at the time was non-deterministic. So depending on the state of the mood of the computer when you booted it, you would get different font rendering, which would throw off all the tests, and they had no error tolerances whatsoever. This thing was absolutely terrible. But anyway, this turned me on to this interesting concept nonetheless. I mean, keep in mind, this was like year 2000. So, we were still in the dark ages. So anyway, I built something kind of like this stochastic test for a quick facility in Go where I would do the state transitions. And what was kind of cool was like after a certain number of iterations on these state transfers, the actual level of code coverage, you can see by the time we hit like about 10 iterations or so, almost hit like 90%. And then when we get close to about 60, it hits 100%. Now, this is not the end all be all for testing, but this was a pretty cool way of like just doing full end-to-end, like let's throw all sorts of junk at this thing and see what happens. And this was all basically driven by quick check in the end. So I have an article that's about halfway done talking about what I did here and how I did. I mean, it's not really, I think, all that useful, but maybe some people who've authored complex systems might appreciate it. So takeaways. If you're already testing with Go, great. This is just another thing for your tool belt. Don't abuse it. Don't overuse it. Like really, like I kind of showed you guys a lot of mundane features here. Most important things are design for testability in the first place, because if you don't do this, you're not going to have a good time. I don't care what your testing tools are, what your harness is, what your framework is, you're not going to have a good time, and you're not going to have fun maintaining your code. This topic has been spoken about, I think, in my opinion, ad nauseum by all sorts of people. My friend Tomasz Szenart gave a nice talk at GopherCon this year called Embrace the Interface, and he talked a lot about the composition with interfaces and using that to aid for testability. And that's a nice thing to fall back on. In the Go world, for those of you new to Go, especially even testing, there's this concept called table-driven testing, where you basically create anonymous table row, or anonymous structs as table rows that define inputs and expected outputs, and you just iterate through that running your test. And it's good. It covers a lot. It covers a lot of bases. But again, let's say you have that probabilistic data structure. The table-driven tests might fall short there. So this is where I think the testing quick comes in helpful. And also, like, really in the end, you want your tests to be simple and you want everything with your test to be simple. So, there's also the topic of how you configure testing quick. The Go doc for that explains everything you need to know. I can let you read that on your own. Are there future opportunities? I told you I have a change list that I'm about to send out for channel generation. I really wish the error reporting with this facility was better. There are cases, like, I promise you, like, if you start using it, like, maybe within a week or so, you'll probably, like, bang your head up against the wall saying, gosh, why am I getting this error here? I don't understand what's going on. And you put some, like, print statements here, and you're like, oh, well, it's because of this. Well, the thing is, there are rough edges with this library. And even though it's part of the standard library, I think it's gotten in, like, probably, I would rank this in, like, the bottom 3 most polished libraries in the standard library. But because of the stability contract guarantee of Go, or Go 1, not much we can do with it. So I want to draft a proposal about how we can make it better for beyond Go 1. I told you this thing for the standard built-in types, it will generate a lot of states. I think right now it will generate maybe about 80% of the possible states for the known built-ins. Core exceptions, I could just tell you right off the top, are, like, let's say you have a slice. Like right now, it won't generate a slice where the length is less than the capacity, or it's nil. Open change list to actually add support for that, because again, those are valid states for those objects, and you might as well know what's happening as an input. For those of you coming from the Haskell world with QuickCheck, you're probably familiar with the ways you could define custom value generators kind of ad hoc. Well, I think there's a lot we could do to improve the way how custom value generation is done, because right now you have to use Reflect, and Reflect is kind of a terrible API, I think. And I mean, it's not as bad as the quick testing quick facility, but it's not so nice. So we can I think as a community, we can make it easier. And lastly, if you have used QuickCheck, you're probably familiar with this concept called shrinking. What shrinking is all about is, let's say you found an input that basically serves as that counterexample for violating the invariant. What shrinking would do in the QuickCheck world is basically you try to reduce that input down to the smallest case where that actually still violates invariant. So basically, you could basically more easily understand why that's happening. So right now, this doesn't do that. I think I saw a change request to add something like this. I don't really know where it stands right now, but that's one thing. So that's all. Any questions? And again, if you want to read this later, voila.